So the first question on the homework asks you to write a general integral equation to find what some total charge is from some infinitesimal charge, and all I really meant there was some total charge is going to be equal to the integral over that charge of dq, right? So if I have some, as an example, some distribution of charge, there's all of these little dq's that make up this distribution, and in order to find what this total charge is, in order to find the total charge, I'm just going to sum all of those little pieces of charge over the boundary. So the next question leads you into how is it that we're actually going to evaluate this integral, because I don't really know how to integrate a dq. I know how to integrate lengths and time, but I don't know how to integrate a dq. So what we need to do is we need to parameterize this dq in such a way that it is in terms of something that we're able to integrate. And the way that we do that is we define two things. One is some infinitesimal, or sorry, one thing is line charge density. You could do this also with area charge density or volume charge density. We'll get to these a little bit later in the semester, but for these types of problems we're only going to be dealing with line charge densities. So we have some line charge density and then some infinitesimal length, dl. Now the way that I have this written here is the most general way that we can write this, because it allows us to ask ourselves what is lambda and what is dl depending on the situation that we're given. So for instance, in the next problem, we're actually going to specifically define what these things are, but they're going to be a little bit different depending on what the problem is. So if I have some infinitesimal charge that's spread over the x-axis, dl is going to be dx. If it's over the y-axis, what should it be? dy, right? And if it's over the arc of a circle, it should be rd theta. Good, good. And we'll get to some of those examples. But for now, the example that I have here was I wanted you to find some total charge. If I tell you that lambda as a function of x is going to be equal to lambda 0, don't remember what I wrote here actually, lambda 0 x divided by a. And that this charge is spread presumably from x is equal to 0 to x is equal to a. So we could draw what this looks like. This is the positive x-axis, and we have this charge that's spread here from x is equal to 0 to x is equal to a. And what we want to do here is we want to find what the total charge is. And so in order to do that, for any one of these types of problems, we need to identify what lambda is, and we need to identify what dl is. In this case, I explicitly tell you what lambda is, and then we just need to write down what dl is. As I alluded to here, dl is going to be dx, and so now we have all the pieces that we need. We can plug everything into this equation, and so we say that q is equal to the integral of dq, which is equal to the integral, and this is over the total charge, which is equal to the integral of lambda dl, which is equal to the integral of lambda 0 x divided by a dx from x is equal to 0 to x is equal to a, right? And we all know how to integrate just some straight line. That's what this is. This is y is equal to x essentially. And so what that tells us in the end is that q is going to be equal to lambda 0 a squared over 2a, where this is going to be equal to lambda 0 times a. Okay? Any questions about that? I think it's pretty. Over 2. Say again?
Over 2?
There's 2.
In the final answer. In the final answer.
Oh, sorry. Yeah, lost my 2 there. Good. Any other questions about this aside from my inability to do algebra? Yeah.
So lambda 0 is always just going to be that charge we're told is spread over the over the line?
Well, yeah, so I threw this under the table a little bit here. What is lambda 0? Lambda 0 is some constant that is dimensionally proportional to charge per length. And the reason why I say that is because this side of the equation has to be charge per length, right? That's by definition what lambda is. X divided by a is dimensionless because this is a length over a length. So dimensions of this are going to be a charge per length, and it's just some constant. Now, I could have done this slightly different for the way that I define this problem. I could have said lambda as a function of x is going to be equal to some q times x divided by a squared, right? That's another way that I could define it, but the important thing here, and why I had this lambda 0 here in the first place, is a matter of dimensional analysis, right? So that the units of the left side are going to match the units of the right side. Okay? Any other questions about this one?
Can you run through why is x over a again?
Yeah, so this was just a choice that I made for this. And the reason why I say this is x over a is because this has, x is a length, right? A is also a length.
So a would be like the
Yeah, a is this.
x is just the length?
Yeah, x is some arbitrary length. Yeah.
So even though if that started like in the negative x-axis and moved through there, would that still be like a negative x or just?
This is still just x. So this is a good question. This is a good question. So what if I said instead of spreading this from x is equal to 0 to x is equal to a, I say I'm going to spread it from x is equal to minus a to x is equal to a. What is that going to change here? Well, the lambda charge density is still exactly the same. It's still this lambda 0 x divided by a, and what that would mean really is that the charges that are over here are going to be negative and the charges over here are going to be positive. But where this x is equal to minus a comes into play is my limits of integration.
Okay, so that's just a lower bound?
Yeah,
okay.
Yeah. And actually the interesting thing that you would see here, if I did this, what's going to happen to this if I do spread this charge density lambda 0 x over a from minus a to a? What should the total charge be? 0. Why? Yeah. There's a couple of ways to say that, right? It's going to cancel out. This is integrating an odd function, so something that's symmetric across the origin over an even interval, right? So that's what I'm integrating really is that. Right, so those are going to cancel. The physical way that we can think about this is the charges over here are negative, the charges over here are positive in exactly the same amount. So they're going to cancel. Good.
So just hit one more time. The x is the total length between the 2 points.
X is just a position.
Okay.
X is just a position. When we get to the length between points is actually going to lead into the next question, because that's kind of getting into what the meaning of R is. Yeah. Okay. So let's talk about that one. So for this question, what I say is I tell you that I have some charge of, let me scroll this so we can see the whole question. I tell you that I have some charge of 2q that's evenly spread from x is equal to 0 to x is equal to a. So we could draw this. So this is, and I'm going to have some point B over here. So this is x is equal to 0. This is x is equal to a. And I'm taking this 2q and I'm evenly spreading it over this region from x is equal to 0 to x is equal to a. So the first thing that I think I asked was to find lambda, right? So we need to find in this case what lambda is. So we always come back to, I skipped the question, right? I skipped the infinitesimal force equation. So let me write that up here. So the infinitesimal force equation looks almost the same as the regular equation for the force between 2 point particles. The only difference is that you have an infinitesimal force and an infinitesimal charge. So that's to say that dF is going to be equal to 1 over 4 pi epsilon naught q dq divided by r squared times r hat. Okay, and I slightly changed the notation. We were talking about these from 1 to 2, but that's assumed here. This dF as a force points from the dq to the q. It's a force that dq acts on q, and r hat, the unit vector, points from dq to q. Okay. So now what we want to do is we want to actually use this equation to find what some force is on some charge, let's say is capital Q minus Q. That is some charge minus Q on the positive x-axis at a point B. So the first thing that we want to determine here is what the charge density is. What is lambda? Well, lambda by definition is the charge per length. And so if I tell you that I have some total charge 2q, and it's evenly spread from x is equal to 0 to x is equal to a, this just says that this is 2q divided by a. Okay. The next thing that we want to do is determine what dl is. In this case, because this is spread over the positive x-axis, this is the same as it was in the last problem. dl is equal to dx. Okay. The next thing that we want is to determine the distance from one of these dq's to the point where we're finding the force, to the minus q. And like I said, this was the part that's a little bit tricky, and I think this was getting at what you were asking. Every single one of these dq's is going to be at a different place, right? Because it's over the distribution. There's one here and here and here and here. So when we parameterize the distance that is from the origin, what we need to do is we need to say that this is some variable. They're all at slightly different positions, but we can call the position that it is on the x-axis just the distance x. And what we're trying to find is this distance r. Remember, r is the distance from dq to minus q. And so in order to do that, we just need to take into account that this is going to be some total distance b. And so r is just going to be equal to b minus x. Okay? Now, the next thing that we need to determine is what the unit vector is. What is the unit vector that points from dq to minus q? What do we think?
Positive.
Positive x hat, right? This is just our r hat. So r hat is going to be equal to positive x hat. Okay? Now, all we need to do is put all of this together in the equation that I wrote here, and I'll integrate both sides. So what we can say is that the force is going to be equal to 1 over 4 pi epsilon naught, and I'll do this in a couple of lines so that you can see all the steps. So this is going to be 1 over 4 pi epsilon naught, the integral from where to where? Where are we integrating from and to? 0 to b, 0 to x, x to infinity. There's some options, right? But there's a physical meaning for this integral, right? What am I doing when I'm integrating these dq's?
Adding all the dl's.
Yes, I'm adding up all the little pieces of dl that make the dq, right? And so when we look at what the limits of integration are here, it has physical meaning to where the charge is. Where does the charge start? Where does the charge end? Right? So when we look at where the charge starts, that's going to be x is equal to 0. And where it ends is going to be x is equal to a. Okay, so then we have our q dq over r hat, which is going to be equal to 1 over 4 pi epsilon naught. I'm running out of room here a little bit. This is x is equal to 0 to x is equal to a. We can plug in our dq is equal to lambda dl, plug in lambda, plug in dl, and so that's going to give us 2q over a times this q, which I said was minus q, so this is minus q, times our dl, which is dx, divided by r squared. So this is r squared is going to be b minus x, quantity squared. And because I don't have room here, I'm just going to sneak my x hat out in the front. Okay? And if this was a problem on one of our exams, this is where we would stop. So I just want you to obtain an integral that can be solved. And the only types of integrals that I will actually ask you to solve are of the form x to the n dx. Or I think I might have you do e to the x, e to the ax dx, and the integral of cosine of theta, or not divided by, but you can understand that I'm saying cosine of theta or sine of theta d theta. These are the only types of integrals that I'll actually ask you to evaluate. Anything else, it's good practice. You can do this to check your answer, because what's important about this is what should the direction of the force that acts on this ultimately be? So we have a positive 2q and a minus q here. It should go to the left, right? Because this is going to attract it. So when I evaluate this integral, if I've done everything carefully, I should end up getting something that's negative. Okay? Yeah?
Why did you square the denominator b minus x?
It's because r is squared here. Yeah.
Why do you have a x hat instead of minus x hat?
It's an x hat because by definition, r hat points from dq to this q. And remember, the way that because I think part of the reason why you're asking is because we know the direction of the force should be this way, right? That comes out in the end because I'm plugging in the value of the charge. Yeah. So like I said, there are a couple of different notations to do this. One of them is to take the absolute value of the charges and then do the unit vector as what the direction of the force actually points. My preference for doing these, and for the notations, I think that one's not one of the worst. There are worse ways to do it. But for my preference for the notation, and part of the reason why I do that is because what is a vector? A vector is something with magnitude and direction. So when I look at this equation, this is the magnitude and this is the direction. Everything's separated very nicely. So that's one part. And then the other part, the reason why I don't take absolute values is I prefer not to unnecessarily take absolute values if I can evaluate the equation in a more general way that gives you the right answer without having to add that extra step. But ultimately on an exam, regardless of the way that you do it, as long as you come up with the right answer and all of the arithmetic is consistent, I'll give you full credit, whether you do it the way that I do it or not. But for the way that I'm defining things, that's the reason why this is positive x hat. Yeah.
Why is the r not squared in the first form of the?
It's because I missed it. The king of the factor of 2's that I'm missing here. Okay. All right. Any other questions?